In this video, we're going to look at finding the complex zeros of certain polynomials and certain issues related to this. So, first question, we've got a polynomial f of x equals x cubed minus 7x squared plus 17x minus 15, and we're trying to find all of the complex zeros. Essentially, we're going to factor this polynomial. So, the first thing I'm going to do here is I'm going to go looking for rational zeros. So, I can use my rational root theorem, or use the rational root theorem. I can find possible or maybe potential rational zeros. And what I get is plus or minus. Now, these have to look like a factor of my constant term, 15, divided by a factor of my leading term, which is 1, or the coefficient of my leading term. Leading coefficient, that's 1. So essentially, if you think about that, that means that, let's see, factors of 15, I could get 1 over 1. I could get plus or minus. Another factor of 15 would be 3 over 1. Another factor of 15 would be 5. Whoops, not over 15. Sorry. Over 1. Another factor would be 15 over 1. So that's really plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So we have 8 possible rational zeros. Essentially, to be honest, if those don't work out, I'm a little bit lost of what to do here. I guess there is a formula for finding zeros of degree 3 polynomials, but that tends to be tricky. So I'm expecting one of these at least to work out, probably either 1 or 3, because if 1 works out, then I can use quadratic formula to find the other 2. So let's go try that. Okay, so I'm going to open up my calculator, and I'm going to essentially plug in these possible roots to see if they're actually zeros of this polynomial. Before I do that, I'm going to enter the polynomial in. So I'm going to go to y equals, and I'm going to do x to the third minus 7x squared plus 17x minus 15. I can enter that in. And now what I want to do is evaluate this polynomial at plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Could use the table to do that. Let's maybe look at that. Here, so I do the table. I look down and, oh, actually I see if I plug in 3, I get a 0. So the table does that. You can also arrow up with the table here. Maybe I should check everything. There's 5, no zeros. I want to go up to 15, nothing there. And I want to go up to negative 15. And I probably want to go down to negative 15 as well. Let's see. We found this getting bigger. Doesn't seem promising, but yep, no zero. So the only 0 we had, I believe it was positive 3, but I kind of forget. So let's make sure. Yeah, it was positive 3. So this calculator tells us that x equals 3 is a 0. Okay, so that's 1 0, but this is a degree 3 polynomial, so with multiplicities, I should get 3 zeros, and I only have 1. So there's 2 more that are missing, or maybe 3 is a root of degree higher than 1, or multiplicity higher than 1. So maybe this is actually x minus 3 cubed. Turns out that's not the case. Okay, so how do I find the rest of these? Well, what I'm going to do is I'm going to take my x cubed minus 7x squared plus 17x minus 15, and I'm going to divide by x minus 3, so x minus the root here. And that will give me sort of factor out the x minus 3 and just see what's left. I know that will be a quadratic, so worst case I can use the quadratic formula to find the rest of the roots. So I'm going to do my long division. X times x squared gives me x cubed. X squared times x is x cubed. X squared times negative 3 is negative 3x squared. And I want to subtract this. X cubed minus x cubed is 0. Negative 7x squared minus negative 3x squared is minus 4x squared. Here. Let's get some more space. And then x times what is negative 4x squared? That would be negative 4x. Negative 4x times x is negative 4x squared. Negative 4x times negative 3 is plus 12x. Subtract. Get a 0. 17x minus 12x is 5x minus 15. And then x times 5 should give me 5x minus 15. If I subtract this, I get a 0. Because I knew x equals 3 is a 0, I should get a remainder of 0 here. If I don't, it means either x equals 3 was not a 0, or I made some kind of mistake in my long division here. So it's a nice check there to make sure things went okay. Okay, so what we've got here is our f of x, which was x cubed minus 7x squared plus 17x minus 15, I've already started to factor this out as x minus 3 times x squared minus 4x plus 5. So now all we need to do is find the roots of x squared minus 4x plus 5. Typically, I'd sit here and try and factor this a little bit in my head, maybe find some nice whole numbers. That's not going to work out. And actually, if it was, I would have found zeros of plus or minus 1, 3, 5, or 15 when I went through the calculator and looked for zeros here. So I know right away this isn't going to probably factor nicely. So what I'm going to do is use the quadratic formula. Again, my quadratic formula tells me that really my zeros of x squared minus 4x plus 5. So I have x squared minus 4x plus 5. My zeros, so if that equals 0, I have x is, okay, the formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. And then a would be the coefficient of x squared, that's 1. B would be the coefficient of x, that's negative 4. C would be the constant term, that's 5. So we get here, let me move my equals down a little bit. Negative b is negative 4, that's plus 4. Plus or minus the square root. B squared, that's negative 4 squared. Minus 4, a is 1, c is 5. Divided by 2 times 1. So we get 4 plus or minus square root. 4 squared is 16. Minus 20, that gives me minus 4 over 2. And what I get, let's see, is then 4 plus or minus square root of 4 is going to be 2, but then I have a negative, so that's going to be 2 times I over 2. And then this is 4 over 2 plus or minus 2I over 2. That's 2 plus or minus I here. So those are actually my other two zeros. So I found all three zeros here. So my zeros here, which is what this question asked for, we had the x equals 3 from above. You have 2 plus I, and you have 2 minus I. Note these two zeros came in a conjugate pair, same complex number, just changing the sign on the sort of imaginary part here. Okay, so that's fine. Again, we actually had to factor this, and sort of here's our answer. Now let's think about what this means for the graph. Question didn't ask for that. But we've got a degree 3 polynomial. We have one real root, and then 2 imaginary roots. So that means that the graph of this function should cross the x-axis one time. So let's just verify that here. If I go to my graph, it should cross at 3 as well. So there it goes. It crosses at 3, and you can see that as you go along. So we could have graphed this right away, seen about where the root is, would have told us which one to guess, and it tells us it looks like there's one root here. But you don't need to do that here. Next question. Let's see. So now we're going to find all of the complex zeros of this degree 4 polynomial. I'm going to start this the same way as the previous one, use the rational root theorem to find possible rational roots. Let's call them potential this time, although that's an arbitrary choice of word. So my potential rational, that is really fraction roots here. And what I get is plus or minus factors of the constant term, that's our 27, or you can think of negative 27, but the plus minus means it doesn't matter whether I think of negative or positive 27. And then I'm going to divide by factors of my leading coefficient, that's the 2. So I'm going to get, let's see, 1 is a factor of 27 over 2. Get plus or minus, I could do 1 over 1. So there's my two factors of 2 is 2 and 1. So I have 1. Next factor of 27 is 3. So plus or minus 3 over 1. Let's be consistent. Here, how about plus or minus 3 over 2? And then plus or minus 3 over 1. Next factor of 27 is 9 over, 2, plus or minus 9 over 1. Last factor of 27 is 27 over 2, plus or minus 27 over 1. Now those are my possible roots. It tells me I really only have to go up to 27 to check if this works out. I'm going to use the calculator to do this as well. So let's switch to our calculator. Clear this out. I'm going to put in my polynomial 2x to the 4th minus 5x to the 3rd plus 15x squared. Because if you didn't have the fancy graphing calculator, let's keep going, minus 45x minus 27. If you didn't have the fancy graphing calculator, you could plug in each of these by hand. It gets a little bit tedious. Calculator makes that sort of more automated. We did the table before. I'm going to do that eventually. I just want to show another way to do this. So you could go to, if you hit the variables key, and then you hit right arrow to go to the y variables will be highlighted. Then I want function. I can hit enter, or I can hit 1 because it's option 1. It's highlighted. And then I'm going to do y1, hit enter. So you could like plug in 1/2 here. As you go along, you get 1/2, and that tells me, hey, 1/2 is not a root. And you could just try all of these possibilities as you go along. Probably the table's faster, but note, I have denominators of 2. So before the table, I'm going to go to second table set, start at, how about we start at 0 here. But my delta, I'm going to want halves here. So I'm going to do 0.5s here. Now, sometimes you got to just kind of play around and see what's there. But I'm going to do 0.5s just to show this. So we have 0, we got a 3. So x equals 3 is a root. See, did we find anything else? Can keep going here. Let's see. It looks like this is getting bigger and bigger and bigger. We know we have to go up to 27 potentially. This doesn't look very promising. I might have just given up here. Hope things would work out. And now notice that my emulator goes too quick. And now I want to go back up to 0. So I could arrow up to get to 0, but I'm going to go to table set. Whoops. That's window. Second table set. I'm going to just start at 0 again. And go back to table. And that's just so I don't have to hit the up arrow a bunch of times. And I'm going to go to negatives. There we go. We got another root at -1/2. I'm going to guess that's everything. Technically, I probably need to go up to -27 to check these. And no more zeros. Okay, so none of these are zeros. Note, I checked everything that had a denominator of 2 between 27 and -27. Denominator of 2 or 1. Note, if you did that, you really don't need this list even. You just need to know what the biggest possible roots are, and that is the sort of the constant term here divided by 1 here. So that would work out as well. Okay, so we have 3 and 1/2 here. Those are our roots. Now, our factors here that we're going to get from these, x equals 3 will give us x minus 3. -1/2, if you think about this, is 2x plus 1. So if you plug in a -1/2, 2 times -1/2 would be -1 plus 1. So that one takes a little bit of getting used to how to put that together, but our denominator shows up a coefficient of x, negative gives me a plus, and then that numerator is the 1. Did the same thing here, really. 3 over 1, we have a 1 in front of the x, but we don't write the 1 in front of the x, we don't write the 1 in the denominator for 3. So they're kind of similar. Okay, so these are two factors, our linear factors that we know so far, but this is a degree 4 polynomial, so we're missing 2 more factors. Could be these are multiple roots, or there's 2 more complicated roots. It could be complex, or maybe they've got sort of irrational, like a square root of 2 in them or something. So to find those, what I'm going to do is multiply x minus 3 times 2x minus 1. Sorry, x minus 3 times 2x plus 1. I'm going to get 2x squared. Let's see, first outside is plus x. Inside is minus 3 times -2x is minus 6x. -3 times 1 is -3. So that gives me 2x squared minus 5x minus 3. And then I know this 2x squared minus 5x minus 3 should be a factor of 2x to the 4th minus 5x cubed plus 15x squared minus 45x minus 27. So to find out what the rest of the factors are, I'm going to do the long division. So I'm going to get 2x to the 4th minus 5x cubed plus 15x squared minus 45x minus 27. Do my long division, divide by 2x squared minus 5x minus 3. Kind of get a little bit worried I might make a mistake here, but again, I know if I did everything right, I should get a remainder of 0. That's a nice check on, did this work out okay? Okay, so 2x squared times what gives me 2x to the 4th? That's x squared. I get a, let's see, whoops, not a 2 there. It should be a 2x to the 4th. X squared times 2x squared is 2x to the 4th. X squared times -5x is -5x cubed. X squared times -3 is -3x squared. And then you subtract 2x to the 4th minus 2x to the 4th is 0. -5x cubed minus -5x cubed is 0. That's something minus itself. 15x squared minus a negative is plus 3x squared. That's 18x squared minus 45x minus 27. 2x squared times 9 would give me 18x squared. So I get a plus 9. 9 times 2x squared is 18x squared. 9 times -5x is -45x. 9 times -3 is -27. And note, I got the same thing top and bottom. You subtract, you get the 0 like we were expecting. So my quotient is x squared plus 9. And what that means is our original polynomial, 2x to the 4th minus 5x cubed plus 15x squared minus 45x minus 27 should factor as the 2x squared minus 5x minus 3 times x squared plus 9. So we know the roots of 2x squared minus 5x minus 3. That came from really just x minus 3 times 2x plus 1. Wait, those are the factors, but you could get the roots of 3 and negative 1/2 from that. And then we've got to deal with this x squared plus 9. So we could use quadratic formula again. That would work out. Let's do that and then maybe show another way to deal with this particular example as well. So you could use quadratic formula, and so that when you have x squared plus 9 equals 0, what you get is x equals negative b. B is 0. There's 0x, so you get a 0, plus or minus square root b squared is 0, minus 4a is 1, c is 9, over 2 times 1. So this is plus or minus square root of negative 36 over 2. That's plus or minus 6i over 2. That's plus or minus 3i. So you get your roots are plus or minus 3i here. And so your roots, we're calling them zeros. They are roots, really. But your zeros of your original f of x, you got plus, well, let's just write it as 3i. Got negative 3i. And then we had our 3 and negative 1/2 from before. So you got 4 distinct roots. Okay. Like I said, x squared plus 9 equals 0. There's another way to do this that in this case might be a lot slicker. So you can just kind of solve this equation as it is. Subtract 9 from both sides. And you get x squared equals negative 9. Well, then x, you take a square root of both sides, we give you plus or minus square root of negative 9. Note that's plus or minus 3i. So you get your plus or minus 3i that way. Might be a little faster than the quadratic formula in this case. Get used to this. You can pretty much do that in your head as well. Next one. We want to find all the complex zeros of f of x equals x cubed minus 6x squared minus 16x. Okay. This one has a little bit of a twist here. It's actually maybe going to make it harder because of that twist, but it's probably easier in the end. We'll see. We don't have a constant term. So the constant term is 0. There's no, like every term here has an x in it. What that means is you can factor an x out right away. So I can say I can factor an x out. I get an x squared minus 6x minus 16. If you distributed the x, it would sort of up all the x powers. And now this x, that's going to give us a 0 of x equals 0 here. So if you plugged in 0, each of these terms would be 0. That'd be a 0. We got 1, but there's at most 2 more. And now this one you can actually factor. We'll get x minus 8 times x plus 2. And really we factored this. And so our zeros here of f of x, you get 0. You plug in an x. You get an 8. 8 minus 8 would give you 0. And you get a minus 2. Negative 2 plus 2 gets you a 0. So that one's short and sweet, but sometimes students get confused by this x here. Don't really know what to do, but it's actually pretty simple to work with once you're used to it. Next one. We want to find all of the complex zeros of f of x equals x to the 4th plus 6x squared plus 8. Okay, so this one also has a bit of a special form. I have x to the 4th and x squared. All of my x sort of terms are of even degree here. So I have 4 is even, 2 is even here. So what I can do, let's let, how about u equal x squared? And then this f of x, well, let's not write it as f of x. Let's write it just as x to the 4th plus 6x squared plus 8. Well, x to the 4th is x squared squared plus 6 times x squared plus 8. So this is in terms of u, x squared is u. I get u squared plus 6u plus 8. So I can write this that way. Now, I can solve for u. Here. So what I'm going to get is u equals, well, let's see, negative b, It's negative 6 plus or minus the square root of b squared, 36, minus 4 times a, 4 times a is 1 times c is 8 over 2. And I'm noticing here something I wasn't really smart about this. I could have just factored this up here when I look at this, but let's go through this anyway to show the quadratic formula would work. It's just sort of more work here. So what I get now is I get negative 6 plus or minus the square root. 36 minus 4 times 8 is 32. That's a 4. So I'm going to get negative 6 plus or minus 2 over 2. You could split this up. Negative 6 over 2 is negative 3. Plus or minus 2 over 2 is 1. Here you could have also just done the plus minus on top. And then you get negative 3 plus 1, or negative 3 minus 1. So that's a negative 3 plus 1 is negative 2. Negative 3 minus 1 is negative 4. You got negative 2 and negative 4, and that's u here. Now note, I could have, if I was sort of smart about this, I made a remark that I maybe wasn't as efficient, is that when you had u squared plus 6u plus 8, you could have said this is u plus 4 times u plus 2. Could factor this, I'd get my minus 4 out of the u plus 4, minus 2 out of the u plus 2. But quadratic formula works. It's just a little more work in this case. In any case, we get u is negative 2, negative 4. We're not done, because that's u's. We want x's. So that tells me, really, I've got two families of solutions. X squared is negative 2, and x squared is negative 4. Now what I do is I just take the square root of both of these. So x squared equals negative 2. That's x is plus or minus square root negative 2. That's x is plus or minus square root 2 times I. So I can sort of pull out that negative, square root of the negative as an I. X squared equals negative 4 tells me x is plus or minus square root of negative 4. So x is plus or minus square root of 4 is 2, and then I get 9. So my zeros here, which I was expecting 4 of, let's see, so I should get plus or minus square root 2. So I get a square root 2i, get a negative square root 2i, I get a positive 2i, I get a negative 2i. So they're all actually imaginary here. There's no real zeros. So let's just think about what that, well, let me say that's the answer. But let's think about what that means for the graph here. Well, my graph, when I have no real zeros, means this graph should not cross the x-axis. If it crosses the x-axis, it has to have a real zero. So we can actually see this here. Let's clear this out. X to the 4th plus 6x squared plus 8. Here, let's graph this. This may be way too big here. So I see a little bit there. Let's change our window here. So let's go negative, I don't know, how about 50 to, sorry, not on x. X is fine. Negative 10 to 10. Let's change our y to negative 50 to 50. See how much, whoops, negative 50 to 5. That made things worse. Still graphing. Then I go to window, not 5. Let's do 50. And now I graph. And I see this go here. I notice it's kind of parabola looking. It's not going to be because it's an x to the 4th and a 6x squared. Essentially a parabola here, but it will never cross the x-axis. And I know that because all of my roots are real. And that's one of the reasons we might actually want to be able to factor these polynomials. Not, well, sometimes in applications, we actually, these imaginary roots actually mean something here in certain settings here. But also they may just mean, hey, we know there's no real zeros here. If we know there's a certain number for complex zeros, and so if we find imaginary ones, we know there's no real ones. Next up, we want to find all the complex zeros of our polynomial function. That's f of x is x to the 4th minus 2x cubed plus 6x squared minus 2x plus 5. And we're given a hint here. I is a zero of f. So one thing you might do is sort of what we did before. Let's just plug this in, clear that out. X to the 4th minus 2x cubed. So I'm ignoring the hint for this part here and see sort of why that's maybe necessary even. Plus 6x squared minus 2x plus 5. And then I'm going to enter, and then I'll go to the table. If you think about your roots, they should be at most plus or minus 5 with 1. So I'm going to change my table settings. I want my delta to be 1, so that's sort of my biggest denominator here. And I'm going to start at 0 here. Actually, let's start at negative 5. here, because that's the smallest root we could be looking for, or the most negative. Here, and then I'm going to go to my table. I see no zeros here. And I go to 5. I didn't find any zeros here. So I wouldn't really have anywhere to go trying to find rational roots here. So I have I as a 0 here. But what that means, if you understand how complex zeros work, we have real coefficients. So our zeros, we get I. We also get negative I. So you can change the imaginary part, which is really just the I part. There's no real part. If it was like 2 plus I, I'd get a 2 minus I as well. But if I have an I, I have to have a minus I as roots if all of these factors, or all these coefficients, are positive. So what that means is I can build up a quadratic factor, then divide this out. So my quadratic factor, I'm going to do x minus I times x minus negative I, that's x plus I. Multiply these out, you get x times x is x squared, x times I is ix, negative I times x is negative ix, negative I squared. So I get x squared, ix minus ix goes to 0. I squared is negative 1, so minus negative 1 gives me a plus 1. So this tells me x squared plus 1 should be a factor of this degree 4 polynomial. So then you can divide x to the 4th minus 2x cubed plus 6x squared minus 2x plus 5, divide by x squared plus 1. You should get a degree 2 polynomial for degree 4 divided by degree 2. You subtract. 4 minus 2 is 2. So you get a degree 2 polynomial. Then you could use the quadratic formula to find the other two roots. So we're going to do that. X to the 4th minus 2x cubed plus 6x squared minus 2x plus 5. And then we divide by x squared plus 1. X squared times x squared gives me x to the 4th. X squared times 1 gives me x squared. I was going to write that under the x cubed, but that's the wrong column. Should go under the x squared. Subtract, I get a 0. Negative 2x squared minus 0. I should write my subtract here. Negative 2x cubed minus 0 is negative 2x cubed. 6x squared minus x squared is plus 5x squared. Minus 2x plus 5. X squared times negative 2x will give me a negative 2x cubed. Negative 2x times 1 gives me a negative 2x. Subtract, I get a 0. I get a 5x squared. Negative 2x minus negative 2x is 0. Plus 5. And then x squared times 5 gives me 5x squared. 5 times 1 gives me 5. You subtract and get that 0 remainder, which we knew we should get if everything had worked out so far. That's a nice check on making an error. So what we know then is the polynomial we sort of started with, x to the 4th minus 2x cubed plus 6x squared minus 2x plus 5. Well, we figured out because I was a root that negative I also had to be a root, and then if you multiplied x minus I times x minus negative I, you get x squared plus 1 as a factor. Then once you have that factor, you do the long division, and you get this as x squared plus 1 times x squared minus 2x plus 5. Now, what are the roots of x squared minus 2x plus 5 equals 0? So we got the zeros of x squared plus 1. That was I and negative I. So if x squared minus 2x plus 5 equals 0, turns out here, let's see, that I have no nice factorization. So I'm going to use a quadratic formula. X is negative b, that's a 2, minus negative 2, plus or minus square root of b squared, negative 2 squared, minus 4 times a times c, divided by 2 times a, which is 1. So I'm just, a is 1 because it's 1x squared, b is negative 2 because it's negative 2x, and c is 5 because it's a plus 5. So I get 2 plus or minus square root 4 minus 20 over 2. That's 2 plus or minus square root of negative 16 over 2. That's 2 plus or minus square root of 16 is 4, but it's negative, so I get a 4i over 2. And then I get 2 over 2 plus or minus 4i over 2 gives me 1 plus or minus 2i. So there's my other two roots. So my zeros here were the I we started with, and then it has to have its complex conjugate as negative I. And then we get another pair of complex roots, 1 plus I, 1 minus 2. So there are my zeros. Now, what's that mean in terms of the graph? Well, again, there's no real roots. So something else you could have done before this division is you could have tried to graph the original function. we started with, this x to the fourth minus 2x cubed plus 6x squared minus 2x plus 5, graph that, and it tells you here that you should not have crossed the x-axis. If you did, it doesn't mean you'd get a rational root necessarily, but it means if you didn't get a rational root, that you wouldn't get a negative under the square root. So sometimes those are nice things to do just to check that what you're getting is sensible. Last question. Here, a little bit different. We're going to find a polynomial f of x here such that our f is degree 3 and we have zeros of 2 and 4 minus I. Now for a degree 3 polynomial, we should have 3 zeros. We're only given 2 here. So we know zeros, well, we're given 2 and 4 minus I, but we got to have one more. But anytime we have a complex zero like this, 4 minus I, we should get its complex conjugate, which is you just change the sign on the I. So the other 0 is 4 plus I. If this was a 4 plus I, we'd get a 4 minus I. So that's 4 plus or minus I. Now we can actually build our polynomial, f of x. Maybe this is a little annoying, but the 2 gives us an x minus 2 times x minus 4 minus I times x minus 4 plus I. And my preference, and then you sort of want to multiply this out. I mean, technically, I suppose this is the polynomial, but we'd like to turn this into a polynomial with real coefficients here. And my preference here, oh, I didn't say that. Here I'm assuming, although it does not say, I want to find a polynomial function f of x such that f is degree 3, and I want f to have real coefficients here. So it's a real polynomial here. It did not say that. It should say that. Otherwise, you don't need the 4 plus I. You could do something else, anything at all here, really. And you get a polynomial that works. It just might have complex coefficients if you pick something other than 4 plus I. Right, so if I want to get real coefficients, I'm going to multiply these two together, these second two. So I'm going to leave the x minus 2. I'll multiply that through later. X times x is x squared. X times negative 4 plus I is, let's see, that's a negative 4 plus I times x. Negative 4 minus I times x, and then 4 minus I, so I get a minus times a minus is plus, 4 minus I times 4 plus I. So I get x minus 2, so x squared is negative 4x minus ix, and then I get a negative 4x minus negative is plus I x, and then this one is 4 times 4 is 16, 4 times I is plus 4i, negative I times 4 is negative 4i, minus I times I is negative 1. Write that a little more cleanly. Trouble erasing. Negative 1. Okay. So x minus 2. Oh, I think I lost a parenthesis here on this other one. I need my closed parenthesis here. So we get x squared. Let's see. Minus 4x, that's minus 8x. Let me just cross things out here. Did the x squared, we did the minus 4x, ix minus ix, those cancel. 4i minus 4i cancel. So everything with an I actually canceled. And you have 16 minus negative 1 is plus 1. So that's plus 17. So now we've got something no more imaginary parts. It's all real parts. We should multiply this out here. So I'm just going to do x times each term on the right. X times x squared is x cubed. X times negative 8 is negative 8x squared. X times 17 is 17x. And then take negative 2 times each term. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 8x is plus 16x. Negative 2 times 17 is negative 34. And when we want to collect these together, x cubed, we have a minus 8x squared minus 2x squared. It's minus 10x squared. Let's cross out what we've used so far again. And then we have a 17x plus 16x, that's 33x. And then we have a minus 34. So there is our answer here. We should have a degree, or sorry, we should have a 0 of 2 and a 0 of 4 minus I, and then another 0 of 4 plus I, which is forced if we want real coefficients. So that's an answer. Now, if you wanted to be a little bit maybe of a smart aleck about this, there's actually lots of even polynomials with real coefficients here that have the same zeros. So what you could do is instead of saying f of x equals this, which is probably the answer that you're expected to give, but how boring is that? You could sit here and say, let's multiply this by any number. So if you multiply by 5, it'll scale this. So let's how about multiply by 2? You could say, oh, let's make this 2 times x cubed minus 10x squared plus 33x minus 34. So that would give you a 2x cubed minus 20x squared plus 66x minus 68. Or, let's maybe call it g of x. although maybe another f here. I guess they called it f originally. You should call it f, but we'll call it g of x. You can multiply by negative 10 times x cubed minus 10x squared plus 33x minus 34. So the idea here is that I multiply by some real number out here does not change the zeros, which is really the only information we have. So I get a negative 10x cubed. Negative 10 times negative 10 is plus 100 x squared. Negative 10 times 33 is negative 330x. Negative 10 times negative 34 is plus 340. So you could sit here with this polynomial instead here, or this one. So there's really an infinite family of solutions. This one here is probably what people are looking for. You might have an instructor that you have to kind of argue with to get points for some of these, but technically it fits what's written. I suppose I wrote this one and I didn't say, hey, it should be a real polynomial, so you could even do something with imaginaries technically, but probably they wanted a real polynomial here. So, you know, you can play around with this. I wouldn't recommend that unless you're really confident about what you're doing, and still may not be the best idea for your grade.